Okay, let's get started. So welcome to CSE100, really bright and early. So I admire your effort of being awake this early right after a month-long break. So good job on all of you. So I'm your host, Ryan Dougherty. Just call me Ryan. You can call me professor. I'm not a professor, but I appreciate the compliment. So you know to come here Monday, Wednesday, Friday, 8:35. So if you are happy at waking up really early every day of the week, I have my office hours also right around this time on Tuesdays in Brickyard, and also on Thursdays if you're more sane and you wake up later on Thursdays. So the textbook is right here. Don't get the textbook if you don't think you might need it. The textbook is extremely expensive, and we will not be using anything directly from the textbook. All you need are my slides. So that you don't have to get the textbook, but if you want it, you're certainly welcome to get it if you want to, but it's expensive. The grad TAs are Kuntal. He was a TA for me last semester, so he should be good. Mohammed is a brand new TA, so try to go a little easy on him. Here are the 6 labs. I actually saw today, I had L180 on all of these, but it's actually not right. Some of these have an L130 on them. So please double check to know exactly where your lab is. There are no labs this week, so don't go to labs this week. Labs will start next week. Any questions on the staff info? Okay, so what is the course about? So as you might glean from the title, it's about learning this language called C++ and being able to program and boost your resume or CV or whatever. But the real purpose of this class is not about programming at all. So I actually argue programming is only a side effect of the class. The real key that you should get from this class is being able to solve problems using programming. So we have this incredible hardware right in front of us. Why not leverage it to solve problems that we couldn't otherwise solve? So that's basically what the entire course is about, is understanding how to use this language effectively, this C++ thing, to solve problems that we encountered all the time. So I just have a bunch of course objectives here. So as we go through the class, you'll be able to say, oh, we covered this, etc. Major topics. These ones up here are the ones I absolutely must cover no matter what, but we're going to handily cover them really quickly, namely because that I tried to get to the things that are more interesting and more useful to you, namely the things down here, because I want you to be a lot more competitive in the job market once you say, oh, I know this and this and this about programming, whereas your peers in other classes might not be able to know those certain things. So last semester we got through all of these, and I anticipate we will this semester, but we'll see what happens. Yeah. So any questions about description, objectives, topics? And as you might see, I'm trying to video record these. So I have a playlist on the course website, if you haven't already seen that already. There's no guarantee that I will be able to record. It's never failed in the past, but if I happen to not be able to record one day, you are responsible for knowing what was covered that particular day. But I'll try to record them and put them up soon after class. So assessment type stuff. So there are several things that you'll be assessed on in the class. And the main one is programming projects. So we're going to have 8 programming projects. And what we're going to do this semester is we're going to give you a set of test cases, and then you write your program in C++, and then you just try to pass the test cases. That's basically what's going to happen. And then you'll be graded based on how many test cases you pass. Labs is basically the same idea. So You'll meet once a week in your assigned lab section, and then you'll get some points for attendance and some points for completing the test cases for those also. So there are, I believe, 13 labs, and then the lowest 3 lab grades are going to be dropped. So only the top 10 are going to count. So here's something that is new this semester, but I think is going to be interesting. So trying to understand anything in any class, you need to understand the fundamentals, but also what is actually happening. What are people actually using this for? In this case, C++. What are people actually using this for? So later on in the semester, when we have started to learn some new stuff, I'll assign you to write a short paper based off a recent C++ talk at a conference. So here's an example of a conference, a playlist of videos. So then what you'll do is you'll write a report based off of that, based on what was covered in the talk, how is this useful, your impressions of what was good in the talk, what was bad in the talk, that sort of thing. And then tests, of course. So we'll have 2 midterms, one in late February, one in late March, and then the final in late May. And if you do better on the final percentage-wise than the midterms, then that percentage on the final will replace the percentage on the corresponding midterms. So because I figure, since the final's comprehensive, and if you show that you have learned right at the end, then you have shown that you have learned that material, and so it makes sense to replace the material that it tested on before. Okay, any questions on assessment type stuff? Okay, yeah, so around 5%-ish is for each third of a letter grade, but I adjust this based off of how hard I think I tested the students or how much effort was put into the class. If I see a lot of effort put in the class, I'll lower the cutoffs because I see that you are working hard. But it depends on how things will go throughout the semester. But 95% and above is usually an A+, 90% and above is A, 85 is A-, and all the way down. So here's an email policy. Just follow the policy. Namely, contact me if you have individual questions or on general course things. And then usually you'll contact your TA for pretty much anything else and CC me so that I know what's going on. If you have grade appeals, just follow this protocol right here. If there's a grading rubric, look at it. If you have any concerns, write up your list of concerns and then bring it back, and then we'll regrade the entire thing. So if you just follow what's listed in the syllabus, everything should be hunky-dory. And if you happen to have any disability thing with DRC, please let me know as soon as possible. It's never been a problem before, but I don't want it to actually be a problem. So if you have any testing accommodations that you need, please let me know as soon as possible. But you have to, of course, file with DRC first. Okay, my favorite section to talk about, and everyone else's too. So if you notice this box right here, it says that I've issued 28 academic integrity violations. Before last semester, what do you think that number was? 12. So last semester I issued 16 violations, even though I went fully in depth on academic integrity stuff. So what is okay? What is okay is I want you to talk to everyone in this class about general strategies to solve problems, general ideas to solve these problems. So I use this idea, this idea, this, and this idea to solve the problem. That is encouraged. Please do that. I recommend you do that. Please do it. But what do you think is not okay?
How to do it.
Namely the implementation. Yeah. Right, copying and pasting programs. I had one case last semester where there was a group of 4 people working together. One of them got up, and they all had their laptops open. One of them went to go to the bathroom or something, left his laptop open, and the other 3 took photos, I think, of the screen of that one student and then use that to copy and paste from that one student. So there's no end to this. So please do not copy and paste code from other people. We will check it, and we have an automated program to check it. It's much easier than you think it is to be able to detect if something's been copied. So general ideas to solve problems, absolutely okay. Please do that. We fully recommend you do that. But what is not okay is getting things from the internet, copying and pasting things from your other students, or anything like that. If you are not sure if you went over the line, don't hesitate to ask. Because if you haven't turned anything in and you ask, oh, have I gone over the line? You cannot be given an academic integrity violation if you haven't turned anything in. So if any questions at all, please, please, please let me know. I don't like filing these. It's not fun for me or the student. And another thing, I have to meet with the student in person to discuss the violation first. And do you think that's fun for me or the student? So if you don't want to meet with me on this sort of thing, please don't do this sort of thing. But of course, all the moral stuff too. Please don't do that. But if you do this, then what will happen is, and I did this for all 16 people last semester, if you happen to do something related to that on a programming assignment, lab, or report, you get a 0 on that, whatever the item is, plus a third of a letter grade drop in addition to that. So if you had an A+ before, the maximum grade you can get at the end of the semester is now an A. You cannot get an A+ anymore. Okay? If it's on the midterm or final, this has never happened with me, but if it happens, you get a 0 on the final, but also a full letter grade drop in addition. Okay? So your A+ now at most is a B+. Okay? So I do take this seriously. I trust you fully until I'm given reason to not trust you. Okay? Am I clear on this? Do you guys have any questions on what is okay and what is not okay? Yeah.
If I was the student that was cheated.
What's that?
If I was the student that they took the photo.
Yeah. So I meet with all students, and in that case, that student was let go because it was evident to me that this person was not did not participate in any of the cheating himself. So there's no reason to punish a student for when they didn't do anything wrong. Another thing. So whenever you write a paper, like an English class or whatever, you always cite your sources. And a thing that's not really emphasized in the CS department is citing your sources too. So in this class, if you use any source of any kind, please cite it. You are not penalized for citing a source. There's absolutely no penalty for citing any source whatsoever. But copying and pasting from a source, even while citing it, is not okay, because that is not your original work. If you write your own original work and say, oh, I got the idea from this source, that is perfectly okay. And I encourage you to please do that. If you use anything from the course itself, you don't have to cite it. If you have any prerequisite knowledge, like, say, Pythagorean theorem, you don't really need to cite that sort of thing. But if you got like an idea for an algorithm from somewhere, please cite it. Yeah, use your own words. Here are some things that are plagiarism, but yeah, use your own words. And then some last minute things, please be professional. This has never been a problem, but I hope it isn't here. If you believe that you are a victim of sexual abuse, here's a resource for you. If you think you are a victim of that sort of thing. I'm a mandatory reporter, so please let me know if you have any issues of that type. But here's a resource for you if you don't happen to want to talk to me about it. And then just follow university policy. Okay, any questions about the syllabus in general? Okay, so if you haven't seen already, if you go to the Canvas webpage, so I'm trying Canvas out for the first time. There may be some bumps in the road, but we'll see what happens. So the syllabus we just went over is right here. Oh, this web page right here is linked to on the Canvas web page. So if you go to Canvas, there should be a link to this page. The only reason Canvas exists is to facilitate all of the submissions of the assignments and labs, or anything else for that matter, as well as record grades. But so all announcements and any other links that are posted are going to be all on this web page. So these are ones that I maintain. So please bookmark this page, and because I will make announcements pretty frequently. Okay, but any other questions at all? Okay, so let's get right into material. Oh, and by the way, I will use every minute of every class because I think it's really important, and I want to maximize the amount of time that you guys are learning things. So let's get right into the introduction of the class. Yeah, oh yeah, go ahead.
Will these PowerPoints be on Blackboard or Canvas?
Yeah, so this link right here is already here. So the lecture slide's right here.
Okay.
Yeah, so it's this intro link right here, and I put the next one up already. Yeah. Other questions? Yeah.
What's your policy on attendance?
Oh, so I don't record attendance at all because it's just way too complicated to be able to handle that sort of thing. I may give some handouts with your name written on the handout, and then you take your version, and that will count as attendance. But I don't formally take attendance like every day because it's just way too complicated. Other questions? Okay, so let's get right into material. So I have here why program, but I want to ask you a different question. Why do we use computers at all? So think about this. Suppose that I'm going to become the president of the United States, and I'm going to say no more computers in the entire world. They're banned. They're illegal. No laptops, no smartphones, no tablets, no computers of any kind. Okay? A lot will obviously change. But are there some things that we can't do now that we could do with computers? So are there some things that computers can solve for us that we now, without computers of any kind, cannot solve, no matter what? Like what? Yeah.
Aren't the majority of integrals not solvable by integral methods? You have to use that numerical ones to estimate.
Well, a lot of those methods came about in like the 19th century and early 20th century. Some of the methods to integrate functions, and a lot of functions are not expressible in terms of easy to use functions like sine and cosine. But I still argue because the algorithms to integrate functions, say on Wolfram Alpha, were written by humans. So could I, in principle, carry out that algorithm to integrate a function? It may take me a long time, but could I do it in principle? Yeah. Is there anything that a computer can do that I can't do? Yeah.
Don't computers, like, can't they also solve the equations for like Bitcoin that normal people usually can't?
Yeah, so for Bitcoin, what happens there is, so I don't understand it fully, but what happens is fundamentally, the computer creates what is called a hash of some transaction that occurred. So this happens with your bank all the time. So they create this thing called a hash, and then they use that hash to store it in their database, for example. But that hash is created using an algorithm. So could I, in principle, do that algorithm myself by hand? It may take me an absurdly long time and maybe a lot of pen space to write, but could I do it in principle?
Yeah.
So is there anything a computer to do that I can't? Yeah.
Well, I'm pretty sure a person could do anything a computer do, but they wouldn't be nearly as efficient. It's like saying,
Yeah.
like with the screwdriver, you could use your fingers, but like, why would you?
Right. I'm not worried about efficiency right now. I'm just wondering about, in principle, could I do it?
Yes.
Right. So there's actually nothing that a computer can do that I can't do in principle. It may take me an absurdly long time, or it may require multiple people, but I could do it in principle. So why do we use computers at all? If we can just do away with them. Yeah.
It's like think about time.
Oh, sorry?
We like fast. They don't-
Right. Computers are absurdly fast, much faster than a human can ever be. But why, other than how fast it takes, why would we use a computer?
Takes out human error.
Exactly. It takes out human error. To err is human, right? Computers are dumb. They're absurdly dumb. They're just given instructions and they execute those instructions, never making a mistake, unlike humans. So that's why we use computers, namely because they're so fast and they don't have any errors whatsoever. So what are the main pieces in making a computer bend to our will, right? We want a computer to do exactly what we want it to do. So how do we actually make the computer do what we want to do? So a computer in general is just some machine that you can send instructions to, which is what the word programmable means here. So it's designed to follow instructions. So maybe one instruction is add these two numbers, or multiply these two numbers, or store this number over here. So instructions like that, really simple things, not like connect to Facebook, that sort of thing. So those are higher level type things than a single instruction. So a computer is just a machine that you can send instructions to, and then it basically does exactly what we ask it to do. It performs those instructions. So a program then is just a set of instructions. That's all it really is. A computer follows these instructions to perform a task. So the computer, when looking at this program, doesn't see anything from this program other than the instructions themselves. We may think of it as maybe integrating some function, or solving some equation, or computing the hash for Bitcoin or whatever. We may think of it that way, but the computer does not see it that way. All it sees are a bunch of instructions. Is the computer smart or dumb?
Dumb.
Very dumb. So it's absurdly fast, but it's not smart like we are. So a programmer then is the person that writes the program. So just to recap, the computer is just the machine that executes instructions, and we can send it instructions. The program itself is just a bunch of instructions that we will eventually send to the computer, and the programmer is the one who writes the program, and then who designs, creates, and tests programs for computers. So the reason why this class exists mainly then is if we take away the human aspect of this system right here, then there's no programmer. And without a programmer, there's no program, which means that there's no program to feed to a computer to perform any task. So our job is to figure out, how do we write programs to solve particular tasks? And that's the goal of this entire class. How do we write a program to solve a problem that we will face? But there are two aspects of programming that we will consider all throughout the class. So there's an art and a science to it. So there's an artistry in that we will be considering ways of organizing how we achieve these tasks. So we have this overall idea, maybe this one giant task that we need to solve, so maybe integrating a function. But then we need to be able to break that down into subtasks, right? So then maybe we will need to say, oh, the first task is get the integral from the user, right? So that's maybe the first task. Then maybe the second task is to parse the integral. Maybe to say, where's the dx in the equation? Are we going to see a du anywhere else in the equation? Is this a multiple integral? Is this an indefinite integral? Who hasn't taken calculus yet? Okay, so you may be hearing terms that you've never heard before, but you can understand that there are certain things that we need to do each step of the way. We can't just say, solve this equation in general. We need to look at individual parts of it and then parse this big task into subtasks and then handle each task accordingly. And then one of the parts of programming is, how do we organize these subtasks together? So which task should go first? Which one should go second? From the first subtask to the second, what format should we expect the second task to be able to get as input? How should we parse the input? So there's a huge part of this that we need to consider. What is the interface that the user should expect? What things should the user be allowed to input? So for example, suppose that I had a program that had me input exam scores. So would -2 be a valid exam score? Maybe. If you're an evil instructor, maybe. But in general, what are the bounds on what is a valid exam score and what isn't? 0 to 100. So we would need to account that take that into consideration. If the user inputs an invalid value, what do we do then? Should we quit the program or should we ask again? So there's an artistry into this in how to actually organize the task that we need to do. How do you display the information? So suppose that we were making a program that is the menu for In-N-Out Burger. That was one of the assignments we did last semester. Make a menu for In-N-Out Burger. And suppose like we're going to print the total amount so that the user knows how much they're going to have to pay. What should the output look like? Well, it should be a $ followed by a dollar amount, dot, how many digits after the dot? 2. What if I had 10 decimal places? Should the user care? No, but are they going to be annoyed now? Right. So we need to think about how we're going to actually display the information to the user so that they can use our program most effectively. Yeah, how the user interacts with the program. But there's in science too. We need to be able to understand what is the language of how we're going to be writing the programs. What things of the C++ language, for example, do we really need to solve this problem? Do we need the really advanced concepts or do we really just need the basic stuff? And there are several ways, as we'll see, of accomplishing the exact same task. Should we use this concept, this one, or this one? And sometimes one has an advantage and sometimes it has a disadvantage. It depends on the scenario that we will be looking at. So there's an understanding of what parts of the language should we use. But also, we want to make sure that the program actually works, right? So we want to be able to test our program, which is what the test cases are for the assignments. And then if there happens to be a bug in the program, could we design the program in such a way so that we minimize the number of changes we have to make? So if we find a bug in the program and we find out, oh, we have to change this over here, this here, this here, this here, this here, this here, and this here, wouldn't that be worse than having to say, I only have to change this one thing, and then now the program's completely functional? So designing the program so that it minimizes the amount of things you need to fix, if you need to fix things, is also something we need to consider. So there's an art and a science to programming. Any questions on these two slides? Okay, so if we want to know how to use the language effectively, we need to understand what thing are we programming for, right? So we're writing programs. So what are programs going to be run on? What machine? not a virtual machine, but more generally. A computer, right? It's just a computer, right? So the computer mainly is composed of several different things that work together, namely the hardware and the software. So the hardware part of a computer is the literal physical part of the computer, right? So we need to understand, how does the hardware work in a computer? So the main parts of a computer are the CPU, and we'll go into each of these in a bit. The main memory, secondary storage, input and output. So these are the 5 main parts of a computer. Okay, yeah. So this is just a pretty picture version of the previous thing, and we'll go into each one of these. So namely, we have some input devices over here of all sorts. Then they're going to be passed in whatever information we glean from them into the CPU, and then maybe the RAM, which may interface with the secondary storage, whatever that is. And then what happens after that? Maybe some computation happens, and then something is displayed to the user via output devices. Usually the screen, which is what we're going to use in this class pretty much. But of course, anything that is sent away from the computer, that is an output device. So it's not just like a literal output of electrons from the screen. It could be something like sending something to a printer or outputting sound, that sort of thing. So what is the CPU thing? Anyone know what the CPU is? Yeah.
The brain.
It's the brain of the computer, yeah. So as we said, it's a piece of hardware, and it runs programs, whatever that means. So what is a program again? Yeah, it's just a bunch of instructions, right? So the CPU, it runs a whole bunch of instructions. That's all it does. So so it has 2 main parts. The control unit. So the CPU is being fed these instructions, but it sees an instruction and says, okay, what instruction is this? Am I going to be adding 2 numbers, or storing a number, or loading a number, multiplying numbers, whatever? I need to be able to decode what that instruction actually is. Okay? So the control unit is responsible for that sort of thing. It retrieves the next instruction, whatever it is, and has to figure out, what is this instruction supposed to do? It doesn't actually do anything other than decoding the instruction. So nothing is actually performed other than decoding the instruction. Yeah, so it coordinates computer operations. But the what happens right after the control unit is what is called the ALU, the arithmetic and logic unit. So I said that some instructions may be, I got to add these 2 numbers. So the control unit says, oh, it's an add instruction. So then what happens is it forwards that information over to the ALU, whose job then is to say, oh, I have an add instruction now. I'm going to actually do the add of these 2 numbers. Yeah, so it performs any mathematical operations. So adding, subtracting, multiply, divide, that sort of thing. So this is just a pretty picture version. So the CPU is this outer box right here. We're going to be given some instructions as input, and then it's going to be fed into the CPU, but what really happens is the instruction is first fed into the control unit, and then if it needs to perform a mathematical operation, which it often does, it's forwarded over to the ALU, and then once the ALU is done doing whatever mathematical operation it needs to do, it sends it back to the control unit, and then the control unit says, okay, what do I do with this result? And it forwards the result depending on what it needs to do. Does it need to store it somewhere? Does it need to save it for a different computation? That thing. So that from the resulting output is what the control unit gets from the ALU if it needs anything from the ALU. Okay? Any questions on how the CPU at a high level works? Thankfully in this class, we won't actually be writing the instructions themselves, but we'll be writing in a high-level language that will be converted into these instructions. But it's important to think about how the hardware actually works. So how does the CPU actually work? So it needs to get that instruction first, which is called the fetch part of the cycle. So we're going to be talking about a cycle right here. It's going to do these 3 steps over and over and over. So it's got to get one of these instructions from main memory. We haven't talked about main memory yet, but it gets it from main memory. Then it's got to decode it. So who's responsible for decoding this instruction? Right, the control unit. So what is the ALU responsible for? Yeah, all the math stuff. You're right, good. Then it generates a signal. Then it executes the operation, whatever it is. So then this resulting output, the result output, is fed into whatever mechanism of the hardware needs it next. So that's part of the execute part. So then so remember, fetch, it's got to get an instruction, decode, which is figure out what instruction it is, then execute, which is forward it to the ALU if necessary, but once it's done, send it off if needed, depending on what the instruction actually is. And then it just repeats this cycle over and over and over, as long as the program keeps feeding it instructions, feeding the CPU instructions. So what is this main memory thing? So if you look on the specs of your computer, you will see that there's like a hard drive or solid state a disk of some kind, and then you see like 8 gigabytes of memory separately from that. So that 8 gigabytes or 16 or whatever number of gigabytes of memory, that is main memory, effectively. So main memory is where pretty much anything that's running is stored right then and there. So if you're running Microsoft Word or Chrome or whatever application, those things are stored in main memory. And then if you're running one of these programs that we're going to be doing, it holds the instructions as well. So it holds the instructions that need to be executed by the CPU, but also any data that's needed. So if you are viewing a YouTube video, so what happens is that the video is partially downloaded, and the frames of that video are stored as data in main memory. Okay, so that's the data part of this. So main memory holds instructions and data. From the computer's point of view, instructions and data are exactly the same. It doesn't see anything differently from anything else. All it sees is just instructions. It's just bytes, and we'll get into bytes in a bit, but it just holds instructions and data, whatever those are. So when you turn your computer off, main memory is actually wiped. So it's what's called volatile. So you may wonder, why do we even have solid state disks, or why do we have hard disks when we could just use main memory for everything? This is the main reason why. Because if you turn your computer off, everything in main memory gets wiped away. Whereas if you put it in secondary storage, it stays there. Yeah, so that's one of the reasons why we don't use main memory to store things when computers are turned off. Another reason is that it's called random access memory. So if you see RAM anywhere, like 8 gigabytes of RAM, 16 gigabytes of RAM, this is the same thing. So random access memory, main memory, exactly the same idea. The real reason why this is called random access memory, does anyone know why it's called random access? Yeah.
Isn't it because it just accesses the memory just to use or do instructions?
Right. So it can access any location in memory that it wants, but why is it called random access other than that? Yeah.
Differentiate it from restricted the ROMs.
You're technically right, but what is another reason it's called random access memory? So one of the reasons why it's called RAM is that the CPU should be able to access any part of main memory and have it take the exact same amount of time. So if you have a really far away location in memory, it shouldn't take you longer to access that than a closer location. So that's one of the reasons why it's called random access, but you're right, is to differentiate it from ROM. So main memory, all it does is it holds programs, instructions, and data. So how is main memory organized? So you have heard me say 8 gigabytes or 16 gigabytes, or how many of you have heard of a bit? So most of you probably have. So what is a bit? Yeah, a 0 or 1, true or false. So it's the smallest, it's the smallest piece of memory that you can have. It's just a single location in memory. And all it is a 0 or a 1. That's it. So it could either be on or off. So 1 means on, 0 means off. Binary digit, that's where the bit comes from. And for those of you who are electrical engineers, the on, when it's on, that means that it's at a higher voltage, and when it's off, it means a lower voltage. But you won't need to know that for this class. More commonly, we'll talk about bytes instead of bits, because dealing with individual bits is a little cumbersome to do, but bytes are a lot easier. So a byte is just 8 bits put together. That's all it is. So in main memory, we'll assign what is called an address to these 8 bits. So some 8 bits are going to get some address in main memory. Then the next 8 bits are going to get a different address, different address, different address. So you can think of this like a neighborhood, for example. A house is going to be given one address, and then the next house is going to be given a different address. And every part of the area that is encompassed by one house, that is the exact same address. And it's the same thing here. 8 bits have the same address. Then the next 8 bits have a different address, different address, different address, different address, all the way through. Yeah, so there are millions or even billions of bytes of memory in a computer. So we have billions of bytes of memory available to us with this psychotically fast CPU. Aren't you like really excited to make use of this and solve really interesting problems with this incredibly fast hardware? So this is one of the main reasons why C++ is so attractive. Mainly because it is so fast compared to other languages. So if you really, really need performance out of whatever task you're going to solve, use C++. I actually am not a huge fan of C++, but for my research, some of the problems I need to solve, I need every single itty bit of the CPU I absolutely need. So C++ is the language for me. So thinking about that sort of thing can really help you. So if we want to talk about how to actually store things in main memory, what is the number one thing that we usually store? Well, the number one thing we usually store are binary numbers. So you may think, well, I have Chrome open, and none of that is a number, right? So let's just say go to PowerPoint, for example. I don't really see any numbers up here, right? I just see slides, I see text. I don't actually see a number. Anyone want to prove me wrong? Yeah.
Aren't the colors of the screen determined by a 3D RGB frame?
Exactly. So each color, it's not exactly RGB, but you're on the right track. So each of the colors on here is represented by a multiple set of numbers. So the most common one is RGB, or red, green, and blue. So you specify some amount of red, some amount of green, some amount of blue. And then what happens is that if you happen to zoom in literally onto the display way far in, you can actually see the red, green, and blue diodes of the pixel, of each pixel here. So what about the text on each of these, or the pictures for that matter? Well, the pictures, you can just say, are just the same thing, just multiple colors in multiple places, so those can be represented by RGB, for example. But what about all the text here? Well, those are represented by numbers too. And how are they represented by numbers? So everything that you see on your computer is represented by a number in some way. By a binary sequence of numbers. So a number in binary form. And we'll see how to work with binary in a little bit. So all typical text, so not all text, but pretty much anything you'll deal with is in ASCII format. So each letter is some number between 0 and 127 inclusive. And if you happen to look up, say, ASCII table, and then go to here, if you zoom into here, you can see that each individual letter has a corresponding number here. So like capital A is number 65 in decimal. And then different bases here, we won't talk about those. But the important thing here is that each letter that we're working with is corresponding to some number. So if everything on our computer that we see is literally just a number in some way, we need to understand how binary numbers work. Okay, so can anyone, so look at this. It says if we have n bits to address memory in a computer, we can access 2 to the n memory locations. It doesn't matter what it is. So let's just say I have 3 bits that I'm allowed to use. So I have 3 bits to use. So according to this statement right here, how many items can I address with those 3 bits? 8. So because it's 2 to the 3. Can anyone justify why that's true? Yeah.
You have 8 combinations of zeros and ones.
Right. So in this first location, how many things can go in that one location? It may seem really silly, but how many can go in there? No, just this one location. 2, because it can be a 0 or a 1. What about this one? Again, 2. Is the choice of what's chosen here in the first one independent of what is chosen in the second one? Right, they're completely independent. So if I choose a 1 in the first place, I can choose a 0 or a 1 in the second place. It doesn't determine the second bit. So if I choose 1 here and 0 here and then 1 here, I was free to choose either one of the 0 or the 1 in all 3 places. So the number of combinations then is 2 times 2 times 2, which is 8. But if I have n bits, then it's 2 times 2 times 2 times blah, 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 times 2, which is 2 to the n. Going off of this, how many numbers are between 0 and 127 inclusive? 128. Anyone happen to know what power of 2 that is?
6th power.
It's between 6 and 8, and it's not 6 or 8.
7.
7, right. So from this, you can actually figure out immediately all the numbers in ASCII are represented by a set of 7 bits. So if I give you a 7-bit sequence of digits, binary digits, you could, in principle, figure out what letter that corresponds to, or number, or character in the ASCII table. So how do we actually, oops, I don't know what I did there. All right, so next time we'll be converting numbers to binary. I'll see you all on Wednesday.